Okay, so last time we started talking about curves in R3, how to take limits of these curves and how to take derivatives of these curves. Now that we know all this, we can do the next thing, which is find the tangent lines or tangent vectors to these curves. So what we're trying to do is we have a curve. So we're in R3. Okay. We're in R3. We have some curves, and we would like to find the vector tangent to some point on this curve. So that's the goal. And well, if you think about it, what we need is we need to have the point. So in order to define a line, and instead of tangent vectors, we can think about tangent lines, which have a tangent vector component, which is this r prime. So that's basically what we're going to try to do. And it's actually fairly straightforward once we see this definition, how to either find a tangent vector at a point for this curve, which would just be r prime of t0, or find a line, which would be starting at that point where you want to find the tangent vector. So that's this r t0, you add t times v, which is r prime over here. So that would be, this point is when t is equal to t0. And the tangent vector at this point, which would be v for our line, is going to be r prime of t0. And so the line L is going to be r of t0 plus t r prime of t0. So let's do an example. So let's start with something simpler, which would be, let's imagine our curve r of t is equal to t squared t and 1. So we want to find the line, let's say, at t is equal to 2. So r of t, so let's call this t0. R of t0 is equal to 4, 2, and 1. And r prime of t is equal to 2t, 1, and 0. So r prime of t0 is equal to 4, 1, and 0. So then we get our line. So our line now is r of t0 plus t times r prime of t0, which is equal to 4, 2, 1 plus t times 4, 1, 0. Any questions about this? So whatever this curve looks like, and it's actually not hard to see what this curve looks like. So it's 1 in the z direction. Let me write it here. So RT is equal to t squared t and 1. So if we look at our X, Y, Z coordinate system, we go up to 1 in the Z plane. And then we can think about our Y kind of, well, when we have X is equal to Y squared, okay, we know that this is a parabola. But now between these two, we kind of have a different role. It's Y is equal to X squared, right? If you look at the T squared, second. So this is your X. And this is your Y. So how many Y's? Oh, sorry, 1 second. How many Y's do we need to get to X? It's actually this. We need to take Y and square it, and that gives us X. So because of that, we are going to get something that looks like a parabola over here. Yeah, does that make sense? Okay. So then our line over here starts at the point 1. So 1 in the Z direction, 2 in the Y direction, and 4 in the X direction. So give me 1 second. Yeah, for some reason, when you plug in, okay, so when you plug in 2, you get this number. It kind of hints to the fact that this parabola goes this way. That way, when X is 4, no, it probably is. Okay. Well, no, when X is 4 here, Y would be more. So when X is 2, so when Y is 2, X is 4. Yeah, so it probably goes this way. Yes. Y is X. So X over here is T squared, and Y is equal to T. So in this case, when X is 2, Y would be 4. Okay. So when X is 4, right? So yeah, it should go the other way. So let's see. In this example, so over here, when Y is 2, X is going to be, okay, I don't know. There's something over here that I'm missing. I'm not going to go too much into this, but you go to the point 4, 2, 1, and then you look at this vector 4, 1, 0, which makes sense. It has in the X direction, it is moving 4. So let's go here and say it should look let's say something like this. Again, I'm not sure if the graph looks this way or the other way. For whatever reason, I can't figure it out right now. Any questions about this? Oh, and then you get this line. Hmm. Ah, okay, I got it. It does go the other way. Okay, so yeah, it looks like this. And in this case, when you go 2 in the y direction, so 1, 2 over here, you're going 4 in the x direction, like a parabola. Yeah. So here's your x, and here is your y. So if it looks like this, and you go 2 in your y direction, which would be, let's say here, then you'll be going 4 in your x direction, which would end up being there. Okay, so another example which they give is with this r of t. So r of t is equal to cosine of t, sine of t, and 4 cosine squared of t. So they want to find the tangent vectors at 2 points and then find the line at pi over 4. So cosine of t, sine of t, 4 cosine squared of t. So r of t. Yeah, 4. Again, we want to find this at pi over 4. So again, we need to figure out what r of pi over 4 is. I'm just going to plug that in. So cosine of pi over 4, sine of pi over 4, and 4 cosine squared of pi over 4. Okay, please take a minute and finish this problem. So find the derivative, plug in pi over 4, and then find the line. Oh, pi over 4. So r prime of t is going to be equal to negative sine of t cosine of t and 8 cosine of t times negative sine of t. And so r prime of pi over 4 is going to be negative sine of pi over 4 cosine of pi over 4 and 8 cosine of pi over 4 times negative sine of pi over 4. And then you, again, just put these things together. So you're going to get your line is going to be whatever you got for r of pi over 4 plus t times r prime of pi over 4. Any questions? Okay, one thing I do want to mention about the previous problem is rather than trying to figure out how the shape looks, of course, you can see that this over here, x is equal to y squared. Well, a normal parabola looks like y is equal to x squared. And so when you have this opposite thing, clearly your parabola should be going like this. And so this ends up going like this. And then, like I said, you go to this point 421, which is the point here, some point over here, where y is equal to 4. Well, sorry, where y is equal to 2 and x is equal to 4. Okay, so maybe we should say something like this. And then you just draw a line, and that's this line. And the vector tangent to parallel to this line is this vector over here. Any questions? Okay. So let's continue. And here's a picture that they show us for the problem that we just did. The curve is the one that they show. I believe then that this curve, we saw that it was the intersection of two surfaces. Let me make sure that's correct. Here. Okay, not exactly. But anyway, that curve, you're not expected to know how it looks, of course, but you can definitely analyze parts of it. And again, one of them is to be able to find the tangent line at some point on the curve. And that would be, let's say for pi over 4, we found this point, we get this vector, we can make a line. So another interesting curve that we can look at is this over here, and it's I believe you can get the curve by tracing a rolling wheel. So you don't exactly have to know those type of details, but if you take let's say a bicycle wheel, and you take some point, and then you graph how this point moves as you roll the bicycle wheel. So over here it's high, and then over here it's at 0. So it will look something like this, right? Point, and then like this, like that. If you're just following this one point as time moves, so then it gives you this curve over here. And they tell you that when the radius of the wheel is 1, the resulting sinusoid is given by this curve over here for t bigger than 0. So, okay, we're imagining that we only move forward in time. So they ask us to find the point where r prime is horizontal and non-zero. So that would be these points over here. So find where the vector is horizontal to the x-axis, and find the points where r prime has the 0 vector, and that happens here or here. Okay, and so in order to do this, we just really have to take the derivative and set it so either set it to be 0 or set it to be horizontal, so where the y component is 0. But I'm not going to go into exactly the details because it's not that important. But it is useful to know that those are the type of problems that you can do once you know how to take tangent vectors to curves. Okay, I'm going to skip this proof. And let's continue with integration. So the same way we can take the derivative of each component of our of our curve, we can take the integral of each component of our curve, or we can take the integral of our curve. So that looks something like the integral from a to b of r of t dt is equal to the integral from a to b of the x component okay, and then the integral of the y component and then the integral of z component. Okay, so an example is the integral from 0 to pi of 1 t and sine t. So the vector right now, r of t, is going to be 1 t sine t. And we want the integral from 0 to pi of r of t dt. Well, this is going to be, so the integral of the first component, we get t squared. Sorry, we get t, and then we just put in pi. For the second one, we get t squared over 2, and then we just put in pi. And for the third component, we get negative cosine of pi plus cosine of 0. Right? So we just do each component individually. Any questions about this? So again, I'm moving quickly just because that all of this is very much like Calc 1 and Calc 2. We just have more components, and that's the only real difference. Okay, so and very similarly to the one-dimensional case, if R1 and R2 have the same derivative, then they are constants of one. Then one of them plus a constant will be equal to the other one. And okay. So question that comes up every once in a while on a test, and you'll see it in homeworks, is that you are given so this would be the velocity of your vector, of your, let's say a particle. So let's talk a little bit about velocities and accelerations. So again, you are in R3. So here's your X, Y, and Z. And here's your curve. And this curve is given in the form R of t. And imagine that for every point, it tells you where some particle is. So this is, let's say, t is equal to 1. Your particle is here. T is equal to -1, so on and so forth. So it tells you the position of a particle. Well, then you can find the velocity of the particle. So by looking at v of t, so v of t will be the velocity of this particle at every point. And so that will be r prime of t. And that gives you this vector that we were describing. So over here, it gives you some vector. And the length of this vector will tell you how quickly you are moving. And over here, it gives you another vector. So to some degree, you can think about these vectors as first, what direction do I go if suddenly I leave the path and I just start moving in a straight line? So you go in this direction. And another thing is, how quickly are you moving? And in order to figure out how quickly you are moving, you look at the velocity, the magnitude of v of t. And then finally, you can talk about acceleration, which is just the change in your velocity, how quickly your velocity is changing. And so that's the derivative of v. So a of t is equal to v prime of t, which is equal to r double prime of t. And a type of question that might come up is, I tell you the velocity of, or the vector, the curve that describes the velocity of your particle, and I give you some initial point, and I want you to figure out the position of the particle, or r of t. So I give you v of t and some point for r, and I want you to figure out all of r of t. And that's this question right over here. So r dr dt is the same as r prime of t, which is v of t. So you have v of t, and they ask you to find the location of the particle at t equal to 4 if at r 0, so at t0, you're at 4, 1. So the way to do this, so 1 minus 6 sine 3t. So r of t is equal to 1 minus 6 sine of 3t. And then 1/5 t. So the way, oh, this is r prime of t. Okay, so what is R of t going to be? So R of t is going to be, and you can take these integrals or you can just look at the antiderivative. It's going to be t minus, and then if we put a plus over here and we take cos 3, 2, a cosine of 3t. So what happens when we take the derivative of this? The t becomes 1, and the cosine 3t becomes negative, and the 3 comes out and becomes 6, and we're left with what we have on top, and then plus some constant, c1, because constants would disappear. And for the other one, we have 1 over 10 t squared, right? So what happens when we take the derivative? The 2 comes down, cancels, you get 1 over 5t. Any questions so far? Okay, and then they tell us R at, plus some constant. So plus C2. And then they tell us R at 0 is equal to R at 0 is equal to 4, 1. So 4, 1. So this way we can find the constants C1 and C2. So let's plug in our 0. So R of 0, looking at this equation, gives us 0 plus 2. So we get 2 plus C1. And for the other one, we get 0 plus C2. 0 plus C2. And we know that this is equal to 4, 1. So that tells us that C1 is equal to 2. And C2 is equal to 1. Yeah. Okay, so now what do they ask? They ask what is R at time 4? So R4. Well, that will just be 4 plus 2 cosine. So 4 plus 2 cosine of 12 plus 2, and then 1 over 10, 4 squared plus 1. And that will be, this will be your position at time 4. Any questions? No? Okay. So that's what they show you over here. And this is the last step. And so we see that if you have the velocity and you have an initial condition for your R, you can find R. If you have acceleration and you have an initial condition for velocity and an initial condition for R, then you can find your R, okay? We also have the fundamental theorem of calculus, just now for vector valued functions, but it's basically the same thing. If R of t is the antiderivative of RT, and that's antiderivative in each component, then the integral is just going to be, and this is a vector, and each component is the antiderivative of R of t, and this is another vector. So this all makes sense. And then you have the second part, which corresponds to the second part of the fundamental theorem of calculus from Calc 1, which is if you take the derivative with respect to t of this integral, where you have a t up here, the t just drops right into your R of S and you get R of T. So in summary, for the derivative, we have all the normal rules that we had for the derivative in one dimension. We have two more rules for the dot product on the cross product, but they don't appear that often. But again, it's just the product rule, so nothing really new to learn. We talked about how to make a line, which is tangent to a point on your curve. We talked about how to take integrals and how to use that in order to go from velocity to position and so on. Any questions about this section? So all of this stuff is very much connected to Calc 1 and Calc 2, which is why we're not going to spend too much time on it. And if you have any questions, you can definitely come ask. So the next thing that we want to be able to do is find the length on your curve from one point to the other. So here's your curve. Here's your curve. We want to go to one point here. So let's say this is the point A. Go to another point B and find what this length is from here to here. So what's the length from A to B of your curve? Okay, and that's called the arc length of your vector. And the formula for it is fairly simple, and that's given right over here. So the arc length, you can think about it as you take the derivative, you take the magnitude of your derivative, so that kind of corresponds to your velocity. And you can't think about it that way. Where you're adding up infinitely small pieces of your velocity, and if you do that from A to B, that will tell you the length. It tells you how long it will take for you to get from A to B. And so when you take the derivative, you take the derivative of each component, and then you square it, and you take the square root in order to find the magnitude. So again, the formula is the integral from A to B of the magnitude of r prime of t dt, which when you actually are computing it is going to be the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. And this is the arc length relative to this current parameterization. We can try to think of, we will think about how to capture the length of the curve more directly, but this is based on our current parameterization of the curve. So they tell us to find the arc length of the helix given by this r of t, and we recall that this is a helix because in the x and y direction you have cosine and sine. If you squared them, you would get 1. And so you get the circle, but then in the z direction you have 3t, and so it's going up. So it looks something like this. And they want us to find the arc length from 0 to 2 pi. So this is so our helix is given r of t is equal to cosine 3t sine 3t and 3t. Okay, and then 0 to 2 pi. So first we need to find the derivative of r with respect to t. So that is r prime of t is equal to, so we have negative 3 sine 3t, 3 cosine of 3t, and 3. So now we take the integral from 0 to 2 pi of the square root of negative 3 sine of 3t squared plus 3 cosine of 3t squared plus 3 squared. And now this is going to be equal to, so again, something that appears quite often in multivariable calculus is these squares over here. So this whole thing is going to be equal to 0 to 2 pi square root. And we can take out these 3's, this 3 and this 3, and square them. So we get 9 times sine of 3t squared plus cosine of 3t squared, which is 1. So times 1 plus 9. Okay, and this is going to be the integral from 0 to 2 pi of the square root of 18, which is going to be the square root of 18 times 2 pi. Yep. So that's over here. Any questions about this? So that gives us the arc length from one point to the other. So all we really need to do is we need to remember this formula over here. Okay. So another thing that we can do is we can look at the arc length function, which does not tell us from, it doesn't give us a boundary that we're going to. So we go from A to T. So it's a function that you plug in T, and it tells you what your arc length is up until that T. So it's given in terms of S of T. So you can plug in some T, and this will spit out the arc length up until that T. So for example, in this case, it would be asking for S of 2 pi, right? And we got that S of 2 pi was 6 times the square root of 2 pi. And of course, what you can do is you can take the derivative of S with, so now there's a T up here. So we have S of T. So S of T is equal to the integral from A to T of the magnitude of r prime of t dt. And so the change, so ds over dt, well, by the second part of the fundamental theorem of calculus, this is just going to be the magnitude of r prime of, okay, sorry, this should be, if you have a t there, then this should be, what do they use? U. So U and U. Okay. So now when you take the derivative of s with respect to t, the t up here just goes into every place that you see a u in your r prime of t. So this just becomes r prime of t, and you have the magnitude. So what does this side mean? So this side represents the change of your, the change on your arc length with respect to t, which is just velocity. That's what it is. You change your, you take a little change on your curve, and with respect to time, so you move time a little, it moves you on the curve a little. The amount that the ratio of that is your velocity, which is why, again, another intuition for why the magnitude of your r prime of t is your velocity. In order to prove the formula for the arc length, we don't exactly use this connection with velocity. We take little steps on it. So right here, and I'm not doing the proof, but it doesn't use the concept of velocity. So this is kind of, now that we know what the arc length is, we can figure out what velocity is, and that's given over here. So yeah, that's all we're going to talk about today. Let me know if you have any questions.